Okay, let's get started. What we're talking about now is phase transformations or structural transformations that are driven by deviations from global equilibrium. We change the structure of a material in order to minimize its, the appropriate thermodynamic potential, which is usually the free energy. There are really two ways in which phase transformations are accomplished. Suppose that we begin with this alpha phase, which is a high temperature phase, and we cool the system down so that we reach a region in which it's favorable for it to transform to this beta phase, which is a different structure. It could be a gas, this could be a liquid, there could be two different crystal structures, whatever. And we ask how that transformation can be accomplished. Well, if these two phases are different in symmetry, if you can't just continuously transform one into the other, then there's going to be at least some range of conditions below this normal transition temperature in which this alpha phase is perfectly stable. It's a metastable phase. There's no way for it, if it is a metastable phase, if small deviations don't lower its free energy, there is no way for it to know that it's supposed to be beta. So it's going to sit there as alpha unless a region of beta spontaneously appears. And that can happen by thermodynamic fluctuations in the material in the normal course of events. This method of transformation, where a small island of beta appears as a fluctuation within the alpha phase and then grows until it consumes alpha, is what's known as a nucleation and growth transformation. It proceeds by forming a nucleus of the beta phase, which then grows to consume the alpha. There's a second kind of transformation which happens in at least some systems, in fact in a great many of them. It may well be that as we cool this alpha phase, of course as we cool it below this transformation temperature, it is becoming more and more and more unstable. Eventually it may reach a point called the instability point in which it itself is unstable, it's internally unstable, it can no longer exist. Even small fluctuations cause the free energy to go down. When that happens, then we will get a spontaneous transformation, and the alpha will become something else. Maybe beta, maybe still some third thing, but it can no longer exist, so the transformation will occur by an instability. So the two kinds of structural transformations we need to understand are transformations that occur by nucleation and growth from a metastable state, and transformations that occur spontaneously by instabilities like this. Well, we introduced the nucleation and growth transformation last time. The simple introduction to that is as follows. Imagine an island of beta to form within the alpha phase. For simplicity, imagine it to be a sphere. If the beta is the stable phase, then the creation of a volume of beta will lower the free energy by an amount equal to the change in free energy per unit volume times the volume of the nucleus. However, in order to form that nucleus, we also form a surface, and that surface has a positive energy. Therefore, we have two terms. A volumetric term, which is negative and promotes the transformation, and a surface term, which is positive and opposes the transformation. When the particle is very small, r squared is always greater than r cubed. So there will be a radius that's so small that this delta G will be positive, and therefore it's predicted that the nucleus will not form. If the nucleus were to form and become large, r cubed is greater than r squared, and so the change in free energy would be negative. So if I plot the free energy as a function of the nuclear radius, I get a curve that looks something like this. It has a maximum. That's the work to form the critical nucleus. And a little bit of calculation will show you that that work is for a spherical nucleus, 16 pi sigma cubed over 3 delta GV squared. The volumetric change in free energy is here in the denominator. It will be a big function of temperature because as the temperature goes down, the driving force for the transformation goes up. The surface energy is in the numerator, and to a first approximation, it's independent of temperature. If you want to get real fancy, it isn't, but for our purposes, we can say that it is. So that this barrier has to be overcome, and the rate at which nuclei can form is a function of how often we can overcome this barrier. Now, how often is that? Well, the nucleation rate, as with any rate process of this sort, is the product of two terms. How often do we try to overcome the barrier, and what is the probability that a particular try will succeed? Well, how often we try to overcome the barrier, if you start analyzing particular systems, and people have done this can be a very complicated question to answer because you have to get into precisely the mechanisms by which atoms are added to the nucleus. But whatever mechanism you imagine, you've always got to take an atom from the alpha phase and you've got to put it into the beta phase. So there's going to be some sort of diffusional step involved. So the attempt frequency is going to be thermally activated. I should have corrected this, I'm sorry. It should be temperature rather than time. The attempt frequency will be thermally activated with an activation energy like the activation energy for diffusion. What exactly it is depends on the exact process, but you're going to get a term of this general form. And this activation energy for diffusion is an activation energy that, again, to a first approximation, is not temperature dependent. Its temperature dependence will be relatively weak. The success is governed by the exponent of Arrhenius term in which the activation energy is the work to form this critical nucleus, WH. So that's going to be a term that looks like this. I put them both together and I get the nucleation rate is an equation of the Arrhenius form in which the activation energy is the sum of two terms. A work term, work to form the critical nucleus, which is strongly temperature dependent because of that delta GV squared in the denominator, and a diffusion-like activation energy, which is the first approximation independent of temperature. So here's our expression. What does it tell us? If we now plot the nucleation rate, when the temperature is right at the transformation temperature, delta GV is 0, the work to form the nucleus is infinite, therefore no nuclei can form. You always require at least some undercooling to nucleate a transformation. No transformation actually starts at the equilibrium transformation temperature. It can't, for this simple reason. As you come down in temperature, because delta GV starts getting bigger, this term drops sharply in magnitude. It appears in the exponential, so the nucleation rate starts shooting up. However, you're going to finally get to a point, I'm oversimplifying a little bit here, but only a little bit. You're going to finally get to a point where the activation energy is no longer dominated by the work to form a critical nucleus, but rather by this diffusional activation energy here. When that happens, this is temperature independent, the equation is going to turn around, and the rate of nucleation will go down as we continue lowering the temperature. The net effect, because of the fight between nucleation barrier and the growth barrier, is that we get the nucleation rate is a C-curve. The nucleation rate increases until some critical temperature, then it starts decreasing, and eventually becomes a small number. So this is the nucleation rate. What we care about is how long it takes to get the transformation going, and a very good measure of the time required to initiate the transformation is just the reciprocal of the nucleation rate. How long does it take us to produce one nucleus per unit volume per unit time? Of course, that depends on what we choose for the unit volume and time, but we can do that. It's just the reciprocal of the nucleation rate. If we plot the logarithm of that incubation time, we get a curve that looks like this. And this C-curve is the normal kinetic curve that is used to understand and describe nucleated transformations. When the delta T, the supercooling, is 0, the nucleation rate is 0, so the nucleation time is infinity. Yeah, we can get the transformation to happen if we're prepared to wait the lifetimes of an infinite number of universes to see it happen. As we cool, the time goes shooting down, and it turns around here at the nose of this C curve, the minimum time required to start the transformation. However, there is a finite minimum time required to trigger the transformation, then it gets longer again. That has an important effect. And that important effect is that we can not only control the temperature at which a nucleated transformation happens, in many systems we can suppress it entirely by just cooling quickly enough that we get past the nose of that curve. So the kinetics of nucleated transformations follow these kinds of C curves, and it follows that nucleated transformation can be controlled. Well, let me just say because it's important later. We can do a couple of things here. We can, for example, cool slowly, trigger the transformation up here in the nucleation-dominated region, and control the temperature at which it happens. Alternatively, if, and I'll show you in a minute why we want to do this for microstructural reasons, we would like to have the transformation occur down here on the underbelly of the curve. We can quench quickly, heat back up again, and hold the temperature below the nose of the curve so that the transformation starts right here. So we can control the temperature at which the transformation happens, and by doing that, we can actually exert considerable control over the microstructure that comes out in many important cases. Heterogeneous nucleation. If you have ever had the experience of drinking a carbonated adult beverage in a relatively clean glass, and you look at it, you'll see little bubbles coming up inside. You can do it with a Coke, but Coke releases its carbonation too quickly, so you don't really see it. You look closely, and if it's a relatively clean mug, which means you're not drinking it in any of our local establishments, you will see a trail of bubbles coming up from the edge of the glass. Just a trail of bubbles. They'll be forming at a particular place. Everybody's done this, I see. You'll see a trail of bubbles coming up. If you look real closely, the source of those bubbles will be either a scratch on the edge of the glass, or will be some dirt particle down there in the material. Far be it that the glass should be dirty, but if it is, you'll get that. If you'd like to study that process in more detail, and some people do this, people who like their adult beverages a bit flatter, take a salt shaker and sprinkle a few salt cubes into the beverage. And you'll see bubbles come shooting up from each of the salt cubes as it sinks in the beverage. The reason for that is heterogeneous nucleation. And interestingly, I can't go through the whole story, but the theory of heterogeneous nucleation from dirt or surfaces or things of that sort, was first put out not by a material scientist or a physicist, but by a medical doctor. He was, in the Second World War, charged with trying to understand the disease known as the bends. If any of you are scuba divers or such, you know all about that. You go down in the water, there are tables that say how slowly you must come back up, how long you must decompress if you've been down deep. Because if you come up too quickly, nitrogen that is dissolved in your blood will nucleate in bubbles, and you can have a very painful experience, you can even die from it. This is a big problem with divers, and they were very interested in it. And what the doctor observed was that these nitrogen bubbles were nucleating on blood cells. And he says, why on earth is this happening? And he then produced the first really good published theory of heterogeneous nucleation, although to be honest, like everything else, it's back in Willard Gibbs' original text on thermodynamics from the 19th century, if you read carefully enough. But this is the thing with which it was traced. So what is it? Remember that, putting it all very simply, it's the following. Remember that the barrier to nucleation, the reason the nucleus is hard to form, is because of the surface energy. To make the nucleus, we get energy back from the volume, but we pay energy to create the surface. Now, if we can find a way to decrease the energy we have to pay in order to form the nucleus is going to be a lot easier to form. So the nucleus will form preferentially where it can minimize the cost in surface energy. As a simple example, suppose we're inside a bulk material. Suppose it's a polygranular material. And let's consider forming a nucleus here on a grain boundary. Well, if we form a nucleus on a grain boundary, even if it was a perfect sphere, and we can gain some more energy by giving it another shape beyond our discussion here, even if it's a perfect sphere, it costs us the energy of the surface of the sphere, but we get back the energy of the grain boundary that we've eliminated because the nucleus is there. So it is always easier to form a nucleus on a grain boundary from a thermodynamic point of view than it is in the bulk of the material. Similarly, if you have a nucleus, if you have the opportunity to form the nucleus on a surface, virtually any surface, when you form the nucleus on the surface, you can take advantage, but you can get back the energy of the surface that you have now replaced with the surface of your nucleus. So you get back some energy from eliminating some of the original surface energy of the dirt particle that you created, or the surface that you're nucleating on. So it's always easier to nucleate on a surface or a particle than it is just out in the free bulk. Heterogeneous nucleation is always easier. I mean, the air becomes supersaturated with water. Where do you find the dew? Well, you may find it in the form of fog, but long before that, you'll find the dew coating the grass and the leaves and other such things nucleating heterogeneously, long before it starts nucleating homogeneously in the air. So heterogeneous nucleation is preferred. This tells us that when we are doing a transformation that is in this region, where nucleation is controlling the transformation, where the real barrier is the height of the barrier to form the nucleus, it's always going to be easier to form the nucleus at a free surface, so we're always going to see nucleation preferentially, almost always, at places that allow heterogeneous nucleation. When we form nucleation trigger the transformation with only slight undercooling in a polygranular solid, we will tend to find nucleation along boundaries at high temperature. Other heterogeneities, maybe precipitate particles, things of that sort, will catalyze nucleation. I showed you examples earlier in the course of nuclei growing on other particles inside a solid. That's an example of heterogeneous nucleation. When we nucleate up here with small undercooling, where nucleation is the problem, we will almost always get heterogeneous nucleation. However, if we go down to a much lower temperature, where nucleation is not really a barrier, the barrier is just the growth of the material finding it, then nucleation becomes almost equally likely everywhere. And it is a simple geometric fact that there are many, many more places for nuclei to form within the bulk of the material than there are on the grain boundaries or on dirt particles. So we get the following very important result. If we have a phase transformation, a structural transformation in a solid, let's say, it's going down in temperature. If we let that transformation happen at small undercooling, we're going to get a boundary nucleated process. If, on the other hand, we arrange for that transformation to happen on the underbelly of the transformation curve down here, we will get a much more homogeneous process. Well, how do we use that? The classic way that we use that is in partial phase transformations or precipitation reactions, where we can control where the new phase appears. Here are two examples. This is a situation, this is a 6 nickel steel. We'll see in a minute, martensitic steel has very long linear grains. In this case, we allow the transformation to happen in the nucleation-dominated region, therefore precipitates form along the boundaries of those grains, because those boundaries are good heterogeneous nucleation sites. This is what's called a dark field transmission electron micrograph, in which we light up the second phase, in this case the precipitate phase, and here you see these linear precipitate phases, which are dark in the left hand, a micrograph, and along the boundaries of the material. So by cooling slowly and allowing heterogeneous nucleation to be preferred, we can force the nuclei to form on grain boundaries. Most of the time we don't want that. Most of the time we want our material, our nuclei, to form in the bulk. And we do that by, for example, this is aluminum copper silicon, where we use precipitates to harden the aluminum. It's a classic aerospace alloy. In this case, one does the age hardening reaction like this. We quench the aluminum alloy supersaturated, then heat it up again and age it right here, allowing the precipitation to occur on the underbelly of the transformation curve. The net result is we get a dense distribution of these are needle-like precipitates through the bulk of the aluminum alloy, and as a consequence, since these are barriers to the motion of dislocations, we get a good high-strength alloy. And this is the basis of the aluminum copper precipitation hardened alloys, which are the classic alloys that are used in aircraft. Well, age hardening, I essentially just started describing for you. We particularly use this kind of process in the age hardening of materials like aerospace aluminum alloys, where we form dense distributions of precipitates to control the strength and properties of the material. In order to do that, we must get our precipitates dispersed through the bulk. Precipitates in the grain boundaries are not going to do us any good because the dislocations are moving through the bulk. Not only that, but they're going to do us harm because those precipitates in the grain boundaries can do things that cause fracture. To go along the grain boundaries can cause the material to become very brittle. So instead of getting a material that is strong and tough, we get a material that's weak and brittle. We certainly don't want that. So what do? We start out, let's assume this is not even vaguely as complicated as the aluminum copper diagram, but for the sake of argument, assume this is an aluminum copper diagram. I'm over here on the aluminum rich side, and this is a copper field. Here's a solid solution. I will begin by bringing the material into a temperature within this field, and I will homogenize it there. And that can be a bit of a problem for reasons I'll talk about in a minute. But suppose we now homogenize it at this temperature. To bring out the precipitate, we just want to cool it into this two-phase region. Well, the precipitation reaction is going to be controlled by a C-curve like this. It's nucleated, and therefore I'm going to get this kind of kinetics. So what I want to do, solidify the alloy, homogenize it, quench it originally down to room temperature to suppress intergranular precipitation. Then heat it back up again to allow precipitation to occur here on the belly of this transformation curve so that I get a good distribution of precipitates through the bulk of the material, and that's the classic simple age hardening reaction that is used in quite a few structural metals. I said that we might have some trouble homogenizing a material, and to understand that, I have to talk about the natural heterogeneities that arise when we try to transform a material, particularly going from the liquid to the solid state. To start this process, or almost any other processing of the material, we would like to initially have it in a single-phase region where it's fully homogeneous. How easy is that to do? Well, suppose that we take a material, which is liquid, and we bring it down in and through this two-phase region to form the alpha phase. That's more difficult than you might think in many materials. And in many materials, particularly high-temperature alloys, it's almost impossible to do that. Why? Suppose we start coming down in temperature. We enter the two-phase region right here. The first solid to nucleate has a composition over here on the alpha line. The liquid that's left behind has a composition over here on the liquid line. Now suppose I lower the temperature a little bit further to generate more solid. Well, according to the equilibrium phase diagram, the solid should now have a composition, let's say right here, and the liquid a richer composition, and the liquid will also have a richer composition. The liquid is no problem, but look what has to happen to the solid. In order to change the composition of the solid, according to the phase diagram, we not only have to have new composition of the solid that's now deposited, we have to change the composition of the solid that is already there, that is already formed. This is difficult because it requires diffusion in the solid state. And if the solid is such that diffusion is a difficult process at these kinds of temperatures, that's just not going to happen. So what's going to happen? The original solid will keep its composition. The next solid to form will have its composition, kind of a layer on top. The next solid to form will have its composition, still another layer on top, and so on. So the composition of the successive layers in this inhomogeneous solid will evolve along this solid curve, down the alpha boundary, something like this. At the same time, the composition of the liquid will evolve along the liquid side, something like this. To analyze this process, it's as if every time we formed a little solid, we reached in and took it out of the system so that the composition of the remaining material follows the liquid line. The net result of this is that we end up with a microstructure, which is not homogeneous alpha at all. It is a collection of alpha particles or grains, growing grains, that have gradients within them. Lean and A in the middle, rich in A toward the outside. And in the boundaries between those grains, we have eutectic material, which is the freezing of the last liquid that's left down here. So if you take a fairly stable a solution of a material that is fairly stable, even a copper and aluminum, and you solidify it at any reasonably rapid rate, you do not wind up with a homogeneous solid solution. You wind up with a rather complex material that looks something like this, with heterogeneous compositions within the grains and eutectic material out here along the grain boundaries. That is not good, because this eutectic material will ordinarily have rather poor properties, and it's on the grain boundaries, which forms a continuous network where the material can deform or break. It's also not good because any further processing I might try to do is processing this heterogeneous mess instead of processing an initially homogeneous material. So what do? I homogenize the material. How do I homogenize the material? I take it to a temperature within the alpha field, and I hold it there and let diffusion take its course. In fact, when we did that little problem where I told you, when we solidify, we get a kind of a sinusoidal distribution. This is what I'm talking about in the composition. And we can use x bar equal root 2 dt, that simple little formula, to take a rough guess as to how long and what temperature it's going to take us to homogenize. Now notice something about this homogenization. When you homogenize, you better do your homogenization below the eutectic temperature.